This is a review lesson on graphing quadratic functions. And at the end of this lesson, you should be able to graph a quadratic function, if it's in vertex form or whether it's in standard form. And you should also be able to write the equation of a quadratic function if you've seen its graph. This is particular review for grade 11. It is we work out of the McGraw-Hill Ryerson textbook, which is chapter 3 and chapter 4. And the outcome that we're looking at is RF3 and RF4. Just a few reminders when we're working with table of values and vertex. So if I have an equation y equals x squared, this is considered to be our basic parabola. This is just a rough sketch. Our vertex right here at the origin, so this is the vertex. There is a line called the axis of symmetry, which cuts through the vertex. It's a vertical line that goes through the vertex. And we have, with our parabola, when it's called axis of symmetry, it is symmetrical over that vertical line. If I was to create a table of values based on this information that I have, remembering that y is equal to x squared, pick a value for x, I'm going to say 0. Y is going to be 0. Now I always put that vertex in the middle of my table of values because it is going to be that point that's symmetrical on either side of the vertex. So I'm going to pick numbers above the or to the right of 0 and numbers to the left of 0. And so if I put a 1 in, 1 squared is 1. But because of symmetry, -1 is also going to give me the 1. I put a 2 in, 2 squared is 4. But I also know that -2 squared is 4. 3 squared is 9. -3 squared is 9. So I have that symmetry occurring in my table of values. Using that information is really important for graphing. And I always find my vertex and I place my vertex right in the middle of my table of values. Let's look at a couple of examples. Here I have an equation in standard form. So it's really helpful if it was in vertex form because I could start right where my vertex is. But in this particular case, I don't have that. So I have on the board two ways in which we can do this. If you are using the same textbook as I use, this would come from 3.2. This method will come from 3.3. You do not have to know the specific method. You don't have to learn both of them. You need to know how to do one and to be able to do it. So the PQ formulas, I do have trouble remembering the formulas, so I tend to lean towards completing the square, but P is -b over 2a. And just a reminder that in my quadratic, it's ax squared plus bx plus c equal, or y equals. So then there's my a, there's my b, there's my c, and that's what those letters are representing. So with the value of p, it's -b over 2a. So in this particular case, that would be a -2 over 2 times 1, which is -1. So my p is -1. Well, what I do when I have that is I need to find the value of q. And there is a formula, but basically I'm treating my function like this. And I'm going to substitute in the value of -1 for x into the function. So I have 1 minus 2 plus 3, which gives me 2. So that is actually telling me that q is 2. So what's that vertex? The vertex is -1, 2. So this is just how do you tell what the vertex is. The other method we have is called using completing the square. So I have y is equal to x squared plus 2x plus 3. I'm going to group my terms that have x. So I have x squared plus 2x. And now I'm going to make this a perfect square. To make it a perfect square, I divide my 2x term, my x term by 2, and then square the result. So 2 divided by 2 is 1, 1 squared is 1. But if I add 1 and I need to keep this equation balanced, I need to subtract 1. Because really what I'm doing is just adding 0. Adding 0 doesn't change my value, but when I add 1, subtract 1, which is still 0, it changes how it looks. This trinomial x squared plus 2x plus 1 is a perfect square. I know that because I just made it one. So I'm going to factor that. It's a perfect square trinomial, so x plus 1 all squared. And I have a minus 1 plus 3. So y is equal to x plus 1 squared plus 2. And when I go to identify my vertex is negative 1, 2. Remembering that the sign change. So if I'm looking at it in vertex form, y is equal to a x minus p squared plus q. Right, so it has that negative. So if there's a plus, it means subtract a negative. Okay, what do I do now? So we got vertex two different ways. I'm going to use the vertex. So we know that our vertex is equal to, I honestly don't remember what we wrote down. It was just the last slide. It was negative 1, 2. I like having it in vertex form. So y was equal to x plus 1 squared plus 2. Makes it easier for my table of values, but it's not necessary. I just find that that makes life a little easier. So I'm going to put in my vertex first. So we said negative 1, 2. And we know that it's symmetrical around this point. So that means I'm going to pick numbers below, and I'm going to pick numbers above. That's going to make life easier. So I put a 0 in. I get my y-intercept, which is 3. And just the shortcut here is when it is in the form ax squared plus bx plus c, which we have here, this value is the y-intercept. I put a 1 into this equation. 1 plus 1 squared, so that's 2 squared is 4. 4 plus 2 is 6. I don't have to do the other calculations because of symmetry. I know this is 3 and this is 6. So we can plot these points. So negative 1, 2, 0, 3, negative 2, 3, negative 3. Oh, I missed something. Sorry. 1, 6. And there's our parabola. Here's another example. And I'm going to use it both ways for you so you can model it with the value of P, the value of Q using the PQ formula, or you can complete the square with this one. So here's an example of where you might want to pause and try the answer and then come back into the video to get the answers. So if I look at P and said it's negative B over 2A, so that means it's negative 12 over 2 times a negative 2, negative 12 over negative 4, which is 3. So then into my function that I have, I am going to substitute in the value of 3. And this is giving me negative 2 times 9 plus 36 minus 11. So negative 18 plus 36 is 18. 18 minus 11, 7. So our vertex is 3, 7. So I'm just going to make this a little smaller. So that's one method. The next thing I'm going to do is I am going to use completing the square so you can see that process. y is equal to negative 2x squared plus 12x minus 11. So I'm grouping where the x terms are, the x squared and the x term. Sorry, mixed up here. Because I have a leading coefficient that is not 1, I'm going to factor out the negative 2. So this is 12 divided by negative 2, which is negative 6. And I'm only dealing with the terms that have an x. Now I'm going to complete the square within the bracket. So x squared minus 6x, I divide the 6 by 2 and I get 3, and 3 squared is 9. So if I add 9, I must also subtract 9, because that's giving me the 0. This trinomial is the perfect square. So y is equal to negative 2, and then I have x minus 3 all squared. That's it in factored form. Minus the 9, minus 11. And I'm going to distribute through the brackets. Really not going to have to do anything with the first one because it's onto this bracket squared. So it would be negative 2 onto x minus 3 all squared. Negative 2 times negative 9 is positive 18 minus 11. Y is equal to negative 2 onto x minus 3 squared plus 7. And the vertex is 3, 7. From here, we're going to do our table of values. So our vertex was 3, 7. And I'm going to pick a number. I guess these are going down, and I can pick numbers going up. Put these values into the equation, and it doesn't matter if you use the standard form or the vertex form. And I put in a 2, I get 5, which means that 4 also returns 5. And if I put in a 1, I get a negative 1. And that also means that if I put in 5, I get negative 1. So if we were to plot this, and we have 3, 7, and we have 4, 5, and 2 at 5, and 1 is at negative 1, 5 is at negative 1. We have a parabola that opens down, and it's just a little bit narrower than if I just had y equals x squared. So now you should ask yourself, though, a few questions. Does that make sense? Based on the information that I know about quadratics, should it open down? Yes, because my leading coefficient is negative. We know it's going to be slightly more narrow than an x squared graph because of the 2. So it opens down and it's narrow. So that's a good check just to make sure it makes sense. Right away, if you look at this example 3, you're probably saying, I don't want to have to complete the square for this one. So it is more difficult to have to be able to do that. And then it might be, well, how do I even come up with the vertex, or what information is it going to give? There's a few ways that you can try this problem. You don't have to go to the vertex. You never have to when you're doing a table of values. You just need to find a point, put it in, see what other point it gives you, and you just plot those points. It's just way more useful when you find the vertex. I am just going to do it by trial and error. I've shown you how to use the PQ formula to find the vertex and completing the square. This should be a really just, well, I call it fun exercise to see if you know how to complete the square, but it's not ideal. This is not an ideal condition, so I'm not going to bother going to that extreme today. Usually when I have something like this and I'm just going to randomly pick some numbers to see what I've got, I usually start with 0, because it's going to be my y-intercept, which is 5. And then I'm thinking, okay, well, what if I did a 1? If I did a 1 and all of those are positive, it's just going to get bigger. So it's going to be bigger than 5. I'm not even having to do any math. So I'd like to go smaller than the 0 for my x value, but I have that fraction. And the denominator's 4, so even numbers is going to be probably really key for me. So I'm going to pick a negative 2. And remember, what I'm really doing is I am substituting -2 in for these x values. So this is giving me 1 minus 6 plus 5 is giving me a 0. So this is what I'm doing in my head or on scrap paper. So I tried a -2. I'm going to try -4 next. And when I put that in, I get a -3. So then I try a -6. And I put that in and I got a -4. And I'm like, okay, I'm getting really close to where it's going to bend again, which means I'm finding my vertex. So then I try a -8. And when I put in -8, I got a -3. And I'm like, bingo, there is my vertex right here. And I know that -8 gives me a -3, then I know -10 is going to give me 0, and I know that -12 is going to give me 5. And we can plot that. I'm just going to use the graphing feature on my smartboard to graph it so you can see what it looks like. And I need to move it over. So we have a problem that looks like this. Go to the next example 4. In example 4, I'm asking you to write the equation of this parabola. So this comes from chapter 3. Again, how do we do that? Well, we need to keep in mind our vertex form of our equation, y is equal to a onto x minus p all squared plus q, where pq is the vertex. Well, xy is a point. So from the graph that's given, can we determine the vertex? So the vertex is right here, and that is the point -1, 5. This is the P, this is the Q. And I have a point here, and this point is at 2, -1. That's my X, that's my Y. So we take these points and we put their coordinates into the equation that we have. So I will have -1 is equal to A, my X is 2, subtract the -1 squared plus 5. So -1 is equal to A. This would be 2 plus 1 squared plus 5. -1 is equal to A times 3 squared plus 5. I'm going to subtract 5 from both sides. So I get -6 is equal to 9A. Now I need to divide both sides by 9. And I get -2 over 3 is equal to A. This does not give me the equation of my parabola or my quadratic function yet. But I now can write it like this. I'll put that in black here. Y is equal to -2 over 3 x minus a -1, which is plus 1 squared plus 5. This is the equation that matches this parabola. Well, I should have just gone back. Let's make sure that that makes sense for us. Does that make sense? It looks like it's a little bit wider. How do I know that? Well, if it was just a x squared, my points would be here and here, and then I'd have a point here and here. So we know that it has to be a fraction between 0 and 1. It is a negative, which means it opens down. So we need to take that information and use it to estimate if we're correct or not correct. This one's very similar. Give this one a try. Again, I'm starting with y is equal to ax minus p squared plus q. And I have 2, -3 is my vertex. So this is the p, this is the q. I have the point -2, 5. That's the x, that's the y. So we have 5 is equal to a onto x plus 2 squared. Remember, that's subtracting the -2, and I put it in the wrong spot. That's a common error, so we have to be very careful of that. So my P is 2, so it should be x minus 2. And the x is negative 2. Messed up a couple of spots. Okay, so there's my x. There's my negative 2. Subtract my P, which is 2, plus the Q value, which is negative 3, which is same as subtract 3. Let's see if I got that right. Double check it, please. So 5 is the y, negative 2 is the x, 2 is the p, but remember the negative is in the equation, so we're good as negative 2 subtract 2, and q is negative 3. And we simplify. Adding 3 to both sides gives me 8 is equal to 16a. Dividing both sides by 16, a is 1/2. Our equation for this parabola is y is equal to 1/2 x minus 2 squared minus 3. Opens up a little bit wider, and that's the equation. That's the end of our lesson on graphing quadratics.